So welcome to this class. Just briefly, in the last class we discussed about the different types of pulsing methods, HV pulsing, laser pulsing, and we also described in HV pulsing what is the importance of energy deficit, what do you mean by energy deficit, and in the laser pulsing what is the role of cooling time which governs the shape of the particular mass spectrum curve. Fine. And also we have gone through the estimation of peak temperature during pulsing. Okay. Then once we finish this difference between the HV and the laser pulsing, we also talked about how this ionization process takes place. So especially in the laser mode. So it is a photo-assisted ionization process, correct. So photo-assisted ionization process. Okay. So basically there are three phenomena where we can understand how this ionization of a adsorbed atom takes place. Okay. So the first one is, as I show this particular adsorbed atom, the electron from the adsorbed atom can directly tunnel to the conduction band. Fine. This is the simplest one where this ionization can takes place. Okay. The second path is the electron from the add atom. From the add atom is excited by the resonant absorption of the photon, which is h mu. Okay. And this, due to which this particular electron can go to this position and it can tunnel to the conduction band. This is the second path which the electron can follow it. And the third path which it can follow is it involves the absorption of photon into the material. Okay. So this photon absorption into the material will create excite the electron from the position, which creates a hole. Okay. And the electron from the adsorbed atom will pass through this particular hole, go to the particular hole. So or pass through or the tunnel towards the hole in the valence band. Okay. So the first, second and third, these are the three paths which through which the electron from the adsorbed atom can tunnel through the material. Okay. So this first and the third method is enhanced by the large number of electrons in the material. Okay. And at low temperatures, if it is at low temperature, the number of electrons in the conduction band in semiconductor and insulators are negligible. So in this, the third path is more dominant at low temperature for the semiconductors and the insulators. Okay. But regardless of this path, these three paths for the photo-assisted ionization, the photon induces field evaporation, involves creation of an ion on the surface and its consequent acceleration by the surrounding field. Okay. So this is the broad idea for the laser pulsing. So from the laser pulsing, which is different from HV pulsing, the APT, the atom probe tomography, application of that atom probe tomography got broadened up to semiconductors, functional materials, and also the insulators. Okay. So this is broadly what we have described during the last class. Now we can talk about the HV pulsing. Okay. So as you know, in the HV pulsing, you will have a increase in the voltage at that particular, okay. Okay, in that, so there is a certain frequency where these pulses can be generated. So there will be an increase in the voltage and coming back to the voltage, fine. Now, and you can see that on the tip surface, the atoms which are present on the tip surface, those are all in vibration, the frequency, the vibration, correct. So some of the atoms can get polarized, might be at these locations during the HV pulsing. It is not necessary that the atoms will polarize exactly at the peak of the HV pulsing, fine. So the atoms can get polarized at the voltage of the pulse in these locations, not necessarily at the peak of the pulse, fine. So now this has a direct consequence, okay. So there will be a, because of this particular difference in polarization of these atoms at different locations of an HV pulse, due to which there will be a broadening of the peak, okay. So broadening of the mass, so in your mass spectrum you will see a broadening of the peak, okay, of that particular mass to charge ratio. So for this purpose, to improve the resolution, what we call it as we use energy compensation devices. Technique or device. What is this energy compensation device? It actually corrects the energy deficit. Of during HV pulsing. Okay, so ions, so whatever the ions which are entering at an electric field with a low energy will be deflected first. So ions which is entering the electric field with low energy ions will be deflected first and will have a shorter flight path. Shorter flight path means shorter distance, it will travel the shorter distance, correct. These than the ions which are having a high energy, okay. So means ions which are having a high energy will have a longer flight time, okay. So high energy and low energy, it doesn't mean, it means that the ions which are field evaporated during this particular region of the pulse, and ions which are accelerating or atoms which are polarizing at the location of this particular pulse, okay. So it is possible that the ions of the same mass to charge ratio have a different energies, okay, due to this pulsing, HV pulsing, and due to which there will be energy deficit, okay. So it means that the ions which is having a same mass to charge ratio but different energies can arrive at the detector with similar time of flight. This can be possible, okay, and this particular will only leads to the broadening of the mass spectrum peak, okay. And this of different energies, so the ions which is having a same mass to charge ratio of different energies can arrive at the same at the detector with the similar time of flight is possible by using the energy compensation devices, which is called a reflectron, okay, by using the reflectron. So what is the function of reflectron? It is okay. So we use reflectron. So here the more energetic ions, will have a longer flight path. The reflectron is used to make the more energetic ions to have a longer flight path. Okay, so reflectron is nothing but a electrostatic mirror. So if you see the atom probe reconstruction, now you will have an atom probe tip, you have an electrode, okay, and there will be a reflectron here, and the ions which are traveling in this electrostatic field, it gets reflected here, and there will be a detector here. Okay, so the ions which is having a more energy will travel more into the reflectron and travel back to the detector. Okay, so this particular reflectron acts as an electrostatic mirror made up of succession of planes of progressively increasing field. Electric field. Okay, so from this location to this location, there will be increase in the electric field, progressively increasing electric field. So ions which is having a high energy will travel farther into the reflectron before being reflected. So by this you are increasing the time of flight. Fine. So if you see in the okay, so this is just you can see that this is the needle specimen. Okay, this is your local electrode, and this is called a reflectron. As I told you, this is the succession of all the planes which progressively increasing the electric field. So the ion which is having a higher energy, higher energy, it will actually travel into this reflectron at more distance before being deflected, and will reach the detector at the same time of flight which is having a low energy, and it will be deflected much earlier and reach the detector. So in this way, if you have a pulse, HV pulse, if there is an ion which is actually polarized and accelerated at this region, and there is an ion which is accelerated at this region, but they have a same same mass to charge ratio, the difference in the time of flight can be similar or can be same by using the reflectron. Okay, so these ions and these ions will come to the detector at the same time of flight, at the same time. Okay, so the high energy ions will go farther than the low energy ions before deflection. Okay, so this is the reflectron. Here in the right side, I am showing you a mass to charge ratio. Okay, and these are the number of ions, and you can see that without reflectron, the broadening in the peak is much higher. In this case, the broadening in the peaks are much higher. You can see the chromium, vanadium, manganese, iron, the broadening in the peak is much higher. But after using the reflectron, you can see that the broadening in the peaks got reduced significantly. So it improves the mass resolution. So the main function of reflectron is to improve the mass resolution, especially for the HV pulsing, which compensates for the energy deficit. Okay, so during the pulsing, as I told you, at same mass to charge ratio can have a different energies, but to detect the mass to charge ratio, what we should do is, it should reach the detector at the same time of flight. That can be possible by using the reflectron, which is a succession of planes which are progressively increasing the electric field, and the higher energetic ions will travel more inside to the reflectron in that electrostatic field before being deflected as for the low energy ions, and they reach the detector at the similar time of flight, so that the broadening of the peaks gets lowered, so that it will improve the mass resolution. Okay. Basically it reduces the size of the tail of the mass spectrum of the mass peaks. Okay. Size of the tail. So this particular region is the tail of that particular mass peak. Okay. That size of the mass peak, size of the tail of the mass peak reduces. So this is how we can improve the mass resolution. Fine. So I hope now the instrumentation part of atom probe tomography, the basic instrumentation is covered. Fine. Now what we do is we will briefly go through the important experimental protocols which are needed during the field ionization and the field evaporation. So we'll just go through the experimental protocols for FIM and APT. First we'll talk about FIM, the basic protocols which has to be. So we introduced the field ionization in couple of classes before. So what is the exact procedure? So first thing is there should be a very sharp needle, okay, that creates an intense electric field. Okay. Chamber should be ultra high vacuum, and the specimen stage should be cooled down to cryo temperature. It is about 20 to 80 Kelvin. We'll come to the importance of temperature in coming time. Okay. The second important is after the stabilization of temperature and pressure, a low pressure imaging gas is introduced. Okay. This gas can be the pressure can be in the range of 10 raised to the minus 5 to 10 raised to the minus 6 torr. Okay. So this low pressure is limited, usually it is limited by the maximum acceptable pressure for the MCP plates, multi-channel plates. Okay. Imaging gas can be of helium, neon or their mixture. This depends upon the material under investigation. Okay. And the third important point is the specimen is applied for the DC voltage, which progressively increases until an electric field at specimen is very intense. Okay, which is enough to ionize the imaging gas. Ionization of the imaging gas. Okay. So the DC voltage is applied to the specimen. The fourth thing is the voltage is increased to reach the optimum imaging condition. Okay. So the voltage, the fourth condition is the voltage should be increased to an optimum condition. What is the optimum condition now here? The optimum condition corresponds to what we described before is the best image voltage, or we can tell it is a BIV. Okay, and it means that we can also call it as a BIF. We can call it as a best image field condition. That is called the optimum condition. Okay, so it means that best image field corresponds to the maximum number of atoms to be imaged with maximum contrast. Okay, so usually the best image field, it critically depends upon the imaging gas which is used. So for example, for helium, which is having a ionization energy of 24.6 electron volt, has a BIF value of 44 volt per nanometer. Similarly, for neon, the ionization potential is around 21.6 electron volt. The BIF value is around 35 volt per nanometer. It means that at these voltage conditions you will get a optimum condition for good contrast image on the fluorescent screen. Okay, so remember in one of the previous classes we actually talked about this BIF and BIV value. Okay, and this is in terms of ionization zone size. Ionization zone size, which is a delta 0, that is related to your spot size, the minimum spot size, that is related to your resolution in the film image, correct. So this is the ionization zone size. Now, so that is there are two conditions in this. One is, remember that if electric field is very low, it means that the critical distance xc is very large. If the critical distance xc is large, then the field distribution in the zone may not reflect the structure of the surface with the atomic resolution. Okay, if xc is large, if these are the imaging gas ions, because of this large xc, then the atomic structure on the tip surface cannot be mimicked or cannot be replicated. Okay, so the field distribution in the zone may not reflect the actual structure of the tip surface. If the field surface is too high, if your electric field is too high, then what will happen? There will be a overlap of the ionization zone ahead of the tip surface, or ahead of the atomic structure of tip surface of each atom. Okay, so this overlap of ionization will blur the image. These are the two conditions which are important related to the BIF. Okay, so this is the fourth condition, where the optimum voltage, or where the optimum best image voltage or best image field is the fifth point. Is the sixth point, pulsing. Okay, pulsing also can be used to induce the field evaporation. Okay, pulsing can also be used to induce the field evaporation in FIM. Okay, so how to choose the imaging gas? So this is a very crucial step during FIM, the choose of imaging gas. Usually the imaging gases, what we particularly, this hydrogen can be used, helium, neon, argon, then xenon. Okay, so they have a different BIF values. Okay, so for hydrogen it is around 22 BIF volt per nanometer. For helium it is 45, for neon it is 38, this is around 2, xenon it is around 15. Okay, so depending upon the imaging gas, so for which material we use which type of gas for the FIM microscopy. Okay, usually the rule, usually what we follow is the choice depends upon the choice of gas depends on the material which is going to be imaged. Okay, so the optimum ionization field of gas, the optimum condition is that the ionization, or we can write is a ionization field of gas should be lower than the evaporation field of specimen. Okay, so ionization field of gas, the optimum condition usually which follows is should be lower than the evaporation field of the specimen. If this is not the case, then what will happen is the specimen will field evaporate continuously, and there will be no proper image will be formed. There will be no proper image. The image will not form properly. Okay, so this is the optimum condition. What we follow is the ionization field of the gas should be lower than the evaporation field of the specimen. So for example, helium is selected for most of the refractory metals. Which is having a high electric evaporation field. Okay, and usually other materials, most of the system which use neon, chosen for most of the systems. Okay, sometimes hydrogen can be used for silicon material, and also what we can do is we can use the combination of these imaging gases. Combination of imaging gases. If the specimen has different phases, okay, which different phases means it will have a different evaporation fields. Fine. So you can use the combination of imaging gases as per that. Okay. So this is the basic condition to choose the imaging gas. Fine. So for example, if your phase exhibits a dark contrast with high ionization field gases. Okay, if your phase exhibits a darker contrast with a high IF gas, with high, then it can be imaged as bright phase or bright contrast phase by using a lower IF gas. Okay, so it will create a better visualization of the structure of the tip. Fine. So this is one of the thing which is very important. First, the second is, if the second case is, if your material is having a very high evaporation field material means the tip surface specimen. If your specimen has a very high evaporation field, then and your gas has a relatively lower IF value, what will happen is that it will create it is very difficult to observe the surface during field evaporation. It's very difficult to observe surface during field evaporation. This is why, because as the field increases, the ionization takes place at much farther regions. The ionization of the imaging gas takes place at much farther region. This due to which it cannot exactly replicate the atomic structure of the tip surface. Okay. So, imaging is not precise of that particular atomic structure of the tip surface. Okay. If you have a very high evaporation field with respect to a low ionization field imaging gas, this is another problem which we usually face. Fine. So, a clear image, for a clear image, what we can do is, for example, for tungsten, for the field evaporation of tungsten using, so what we can do is a clear image can be formed by using the high voltage and laser pulsing. Okay. So, it means that for a okay. So, a clear image can be possible when we can use the whether high voltage or the laser pulsing, which induces the field evaporation of the atoms of the adsorbed atoms of the tungsten. Okay. So, if you have a very high electric field of any material, for example tungsten, correct, we can actually use the very high voltage and the laser pulsing, so that you will get an image of good quality. Okay. By this is due to the field evaporation of those adsorbed atoms. If you have a low evaporation field material and it is imaged with a high ionization field gas, this is, if you want to image a low evaporation field material with a high ionization field gas, then this has to be done, this is possible only when the base temperature is kept very low. So, for example, for imaging aluminum via helium, which is having a very high IF value, and aluminum has a very low EF value, then the temperature should be kept at 20 Kelvin. Okay. So, reducing the temperature avoids the departure of atoms from the surface, departure of the atoms on the surface, raising the electric field to reach the raising the electric field to reach the IF of the gas. Okay. So, in this the temperature plays a very important role. In this condition, the temperature plays a very important role. Okay. So, to summarize, what we can summarize is, if your electric if your evaporation field of specimen is larger than ionization field of gas, this is the optimum condition. You will have a better visualization. If you have a very high evaporation field of specimen, then it is very difficult to observe surface during field evaporation. Okay, if it is, then it is very difficult to observe the surface during field evaporation. So for that purpose, what we use is high voltage plus laser pulsing can be used. So this can be for better imaging purpose. If you have a low evaporation field material or specimen, then high ionization field gas, then this can be imaged possible only when the base temperature is kept very low. So it's around 20 Kelvin for aluminum if you image with helium gas. Okay, so all in all, these are the three important conditions where you can use it for imaging, clear and atomically resolved images. Okay. Now, as I told you here, the temperature plays a very important role here. Okay. So, a stable image plus optimal resolution can be adjusted by the base temperature, okay, which is at the cryogenic temperature between 20 Kelvin to 60 Kelvin. Why is it so? High temperatures usually it increases the velocity of imaging gas, okay, gas atoms. So it will degrade the resolution. Resolution is degraded. The second is any species which are present on the tip surface, which are adsorbed on the surface, for example water, H2, chemicals from sample prep, which can that they can contaminate the imaging gas. And due to which they will migrate onto the surface, which can blur the image. Okay, remember this is the species which are present, which are water, hydrogen, which are chemical species from the sample prep. These can affect the image quality directly, which are absorbed. Okay, so they actually contaminates the imaging gas. However, very low temperature also has a problem. It might induce that it might possible that the gas molecules, the gas atoms which are can be physically absorbed on the surface. Okay, at a very low temperature it might possible that the imaging gas atoms can be physically absorbed on the surface. So this is a problem then. Okay, so the specimen is kept cooler than the gas to liquid transition. So if the specimen is kept at a very low temperature or cooled, then the gas to liquid transition temperature of the imaging gas, then it will form a layer of liquid, okay, and that can create the blurring of images. Okay. So the temperature should be optimum, it should not be very high and it should not be a very low temperature, especially less than the gas to liquid transition temperature. So for helium we can keep as a, it should be less than 20 Kelvin. Other gases we usually use higher temperatures, around 30 Kelvin, more than 30 Kelvin, for example for neon. Okay. So now we just talked about the specimens which is having a single element. So if there are alloys, then the temperature can be induced significant changes. So for the alloys, if you change the temperature, changing the temperature can induce significant changes in the image quality. Okay. Changes in the contrast or image, okay, by changing the temperature in the alloy case. For example, if so you can see in this image, yes, in this image you can see that this particular image is taken at 20 Kelvin and this particular image is taken as 80 Kelvin. Okay. So here you can see that in this image, in this location, we do not see any precipitate. Okay, at 20 Kelvin. However, in this particular film image, you can see that there is a contrast which is related to a titanium rich precipitate in an alloy. Okay. So this effect is due to the local change in curvature due to the presence of the precipitate, and this change in local curvature induces an effective, it means that the effective evaporation field EF changes with the temperature, and therefore it differs for different fields and phases, changes for different field or phases. Okay. So temperature is a very crucial, especially also in the alloy case, where depending upon the nature of the precipitate or the phase present, actually the temperature plays an important role, because this is due to the local change in the curvature that effectively changes the evaporation field, and that changes for different fields and phases. Okay. So if you see, for we talked about also the best image field to get sharp images. Okay. So once the temperature, so to get an optimum image, once the temperature is set, then gas is introduced into the chamber, then voltage is applied, high voltage is applied at an increases, and correspondingly there will be a increase in the electric field intensity. Okay. So then after that, if the presence of any oxides, surface contamination are present from the sample preparation, they gets field evaporated first. Okay. So this is due to the presence of oxide. This is due to the local creation of local roughness, or high local curvature due to the presence of these contaminants. Okay. So basically in the step of film, this particular method, this particular stage, usually what we call it is you are cleaning the specimen, cleaning the tip surface. Okay. So then after the cleaning of the tip surface, the voltage is increased up to a value of BIV, which also corresponds to BIF. Okay. And based on this, based on your sample and based on the gas, actually you can use the combination of imaging gas for a metal or for an alloy, and also the temperature, which has a very important role for the image which is having a very high resolution image, which can resolve the which gives the atomic resolution. Okay. So BIF is the, as I told you, is the highest field that enables the ionization of the imaging gas just above the most protruding atoms on the surface. Okay. So it is the highest field that enables the ionization of the most protruding atoms on the surface, where the electric field is maximum locally, while not inducing any field evaporation of the surface atoms. Okay. So during film, you should be very careful that the voltage should be in such a way that it should not field evaporate the surface atoms. It should be enough so that it should reach an highest field which requires which have the enough electric field where the gas must get ionized. Okay. And it will image the most protruding atoms which are present in the surface. There are other parameters which are very important other than these. One is the quality of vacuum, second is the purity of argon or purity of gases. Okay. So purity means if it contains the contaminants, they have a different IF. Okay. And the third thing is counter electrode. Okay. Counter electrode, it means that the distance between the tip surface and the electrode will have a direct impact on the voltage which is necessary to reach the required electric field. Okay. So this is the role of counter electrode. This will have a direct impact on the image quality. So these are the other three factors which we have to be taken care during for getting a good image quality. So here, by changing the electric field distribution around the specimen apex, this changes the concentration of electric field at the specimen apex. Okay. So to form the image, the polarized gas atoms, to form the image, so if you have, so for example, if you have an atom probe needle, if you have two atom probe needle, okay, same sample, and here there is no counter electrode and here there is a counter electrode, correct, and there is a phosphor screen. Now difference between will be there. To form an image, the polarized gas atoms, so if you have a gas atoms on the top, these polarized gas atoms make forward towards the specimen apex. Okay, and this happens why? By successive hops on the surface. So this atom will move in like this on the surface. Okay, these are the successive hops and it moves towards the apex of the tip. Okay, so if you have a counter electrode, then these, so during successive these hops, what will happen? The particular gaseous atom actually loses the energy. It means it loses the velocity. Okay, so farther is the atom, farther is an atom on the near to on the tip surface, more will be the loss in thermal energy. So the farther will be the atom, then as it comes to the apex, the velocity will become slower and slower. So there will be a reduction in lateral velocity. Remember this lateral velocity term as we described in relation to the resolution. This is the one of the three factors which is responsible for the film resolution or the spot size, correct? Lateral velocity. So higher is the spread in the lateral velocity, lower will be the resolution. Fine. So you can see that here, as if there is no electrode, no counter electrode, the atoms which are moving towards the apex, okay, and as it goes on the surface, it loses the energy, thermal energy, and the velocity becomes much lower and lower. So the spread between the lateral velocity will increase. But in the case of counter electrode, as you know that the electric field is concentrated, so the number of hops that that the atoms has to make towards the apex reduces drastically. So what will happen? That the lateral velocity decrease, the spread in the lateral velocity decrease is minimum, which will have a direct impact on the resolution of the image. Okay, so that's why this lateral velocity describes the spatial resolution in the image, FIM image. Okay, so there is a difference between the, if there is a presence of electrode, then due to the intense electric field, the spread in the lateral velocity will be minimum. But if there is no electrode, you can see that the spread in the lateral velocity will be much higher. So your resolution will be affected with this. Okay, so this lateral velocity increases the spot size. Fine. So with this we will end today's class, where we have just gone through the experimental protocols which are necessary for film field ion microscopy. Okay, and we also described the parameters which are required to get an optimum condition where you can get a very highest spatial resolution on the for imaging in the FIM. So in the next class, what we follow is, we will go to the experimental protocols which are required for the atom probe tomography, where we will describe first the mass spectroscopy, then we will see the detection, how detection is carried out, okay, and how we are measuring the time of flight. Okay, so based on this, what are the important conditions or the parameters to be optimized to get a highly resolved atom probe tomographic reconstructions. Okay. So, with this I will end the class, and we will meet in the next session. Thank you.